All right, so the main topic of this unit, and get those things closed, please. I want everyone's full attention up here. Today's a big day. So the main topic is polynomial functions. That's what we're going to start talking about. Where eventually we're going to get to, solving polynomial equations. But for now, we're just trying to understand what these functions are, what the definition is, and we want to explore what the graphs of polynomial functions look like. We'll just start that today. We'll get into more detail later. So what is a polynomial? Well, a polynomial is just a sum of monomials. Now, what's a monomial? Well, a monomial is just a coefficient times a power of a variable. That's it. So it's really just a sum of a bunch of these terms. Each term, here are the criteria for how you would build the individual terms or monomials. What has to be true? A couple things. The coefficient of the variable has to be a real number. Okay, well, big deal. I mean, we don't even know of anything else at this point. We're going to get to some other kinds of numbers later, but it just has to be a real number. But it could be any real number. Could be irrational, so it could be a square root, it could be pi, it could be a fraction. So the coefficient has to be a real number. The exponent, remember, this is going to be a power of a variable. Usually it's going to be x to some power. The exponent must be a whole number. Okay, so it can't be negative. It can't be fractional. It has to be 0, 1, 2, 3, 4, etc. Right? Because remember, the whole numbers are just the integers starting at 0. It's the positive integers plus 0, or whole numbers, right? So give me 1 to 5 on that so far. Does that all make sense? Okay, and we're just adding up a bunch of terms that all have those characteristics, right? So that each term has to have a real number coefficient times a power of a variable where the exponent's a whole number. Okay, any questions on that? Okay, so what else? How do we describe polynomials? Well, the highest exponent of a polynomial determines the degree of the polynomial. So if we talked about like a fourth degree polynomial, then that would just mean that the highest power of x, if x is our variable, the highest power of x would be x to the fourth. What is standard form for a polynomial? Well, the way we our standard form, the way we're going to consistently write polynomials is like this. We're going to write them in descending order of power of the exponents. So the exponents are just going to step down from the biggest value to the smallest value as we walk through the different terms that are added up in the polynomial. Okay? Oops. So, what if we wanted to write this polynomial in standard form? Now, what's the variable of this polynomial? It's not x. What is it? What's the variable here? K. Okay, so we're using k's instead of x's. Big deal. So if I wanted to write this in standard form, it's pretty simple. I just have to rearrange those terms. Which one would have to come first? Yeah, okay, the biggest power, so negative k to the fifth. What comes next? Okay, minus 3k cubed. Plus 8k minus 1. Okay, so what about that minus 1? What's the power of k that goes with that one? We just don't write it, but it's actually there. No, that's k to the... So if we write these invisible powers, k is the same as k to the 1. 0, yeah, because you guys have done some practice with properties of exponents. Anything taken to the 0 power is equal to 1, exactly. And so, this could have been a 3, it doesn't have to be a 1. But it would have been, if that were minus 3, it still would have been multiplied by my variable to the 0 power. Okay, so the constant really is a power of the variable. It's just a 0 power of the variable. And 0 is a whole number, right? Okay, give me thumbs on that. Is that all good? Okay. Okay, so quick summary. Degree of a term is the sum of the exponents of the variables contained in that term. Now, we're not really going to, I'm going to give you just a couple examples of polynomials that use multiple variables like x's and y's, but we're really not going to do that this year. That's something that you'll deal with in the future. If I had something like, for example, what would be the degree of this term? 4x to the 5th. What's the degree? 5, right? Degree is 5. What if I had 3x cubed y squared? What do you think the degree would be? No, it'd actually be 5. Because it's like we're going to combine those variables into one. Like think about the product of those. If those both were x's and I multiplied them together, I'd get x to the 5th, wouldn't I? Well, they're not both x's, so I can't do that, but the degree would still be 5 there. You're just going to add up the exponents of all the variables. Okay, is that a big deal? No, it's really not. We're not going to be doing stuff with polynomials involving multiple variables, but I just want you to be aware of that, so when you do encounter it in the future, it's not such a such a strange thing. And then the degree of the polynomial, remember, that's just the degree of the largest degree of any of the terms. In other words, the biggest power of the variables. Okay, so then here's how we would write the generic form of a polynomial. Now this looks a little strange, but this is something you got to get used to in math. This is how, this is the best way to write a general polynomial function. Now what in the world does this mean? So f of x is a polynomial. The first term is a sub n times x to the n, plus the next term is a sub n minus 1, x to the n minus 1, and so on. What is the degree of that polynomial? It's n, isn't it, right? Because the biggest power of x is n. Every other term after that has a smaller exponent because we're subtracting something from n. Everybody get that? Well, what number is n? The point is we don't know. It could be anything. N could be 3, n could be 100. We don't know. N just represents any polynomial. We call it an nth degree polynomial. Okay? And then each term we're just going to step that power of x down until eventually at some point we get down to x, the last two terms would be plus some coefficient times x to the 1 plus some coefficient times x to the 0, and that becomes what we call the constant, right? The constant is the last term where the variable disappears because it's taken to the power of 0. Okay, does that make sense? You can see how the exponents work there. Everybody get that? They're starting at n and they're getting progressively smaller until eventually the exponent gets to 0. So the value of n for any specific term tells you the exponent. So if I pick this term right here where the exponent is n minus 2, then that's telling me what the exponent is. Based on the value of n, which we don't know, this is going to be that number minus 2. Okay? Well, we need to be able to name the coefficients of all of these powers of x also. And so the way we do that is we use these subscripts. We just make the subscript match the exponent in this case though, right? So x to the n, whatever n is, x to the power of n, the coefficient of that we're just going to call a sub n. What does that mean? It's just going to be some number, right? But the fact that this is an n and that's an n just tells us that they go together. That a sub n is just the coefficient that goes with x to the n. A sub n minus 1, we don't know what it is, but that's just going to be the coefficient that goes with x to the n minus 1, and so on. Okay, when we look at an actual polynomial, those are just going to be numbers. They're not, these just represent numbers. Okay? Everybody Give me 1 to 5 on that. Is that, you getting an idea of what that looks like? It takes a little getting used to, but it's important that you start to see this stuff and think about it. And the more you think about it and the more you see it, the more clear it becomes. Okay? What else? Okay, so what do we call... So the coefficients, right, we just mentioned that. The coefficients are a sub n minus 1, and so on. We call a sub n because that's the coefficient that goes with the biggest power of x. We call that the leading coefficient. Because the first term in the polynomial is called the leading term. The term with the biggest power of x is always the one we write first, so it leads the show, right? It's the leading term, we call it. Okay? I think that's all the vocabulary we need. Okay, so now let's just practice a little bit. So I'm going to give you some polynomials, and I want you to give me, think about these and tell me the degree and the leading coefficient for each one of those. So take that top one. What's the degree of that polynomial? Is it 1? 0. It's 0, right? Because the biggest power of x is x to the 0. There's an invisible, we don't write it, but there's an invisible x to the 0 there. So this is, actually I'll just write the number. Degree is 0. What's the leading coefficient? 4. Yeah, just 4. Okay, how about the next one? What's the degree? 1. Yep, it's 1 because that's the power of x. What's the leading coefficient? What's the leading term? Negative 5x. Okay. Bottom one, what's the degree? What's the leading coefficient? What's the leading term? Okay, you got it. All right, so quick reminder. Term is the, a number or the product of a number and a variable. Maybe more than one variable, but for us, just one variable. Coefficient, we already know that's what's multiplied by a variable, power of a variable. Constant is the term at the end which doesn't have a variable in it because the power of the variable is 0, so we don't write it. And a polynomial, as we've said, is just a sum of terms, each of which involves a variable raised to a whole number exponent and a real number coefficient. Okay? So we're going to look at one quick example here of a polynomial that has x's and y's, and then I don't think we'll see any more of these probably ever. Yeah, you might give you like 1 on your homework or 1 or 2 where you just got to recognize when we're just like becoming familiar with polynomials. But beyond that, when we start actually doing stuff with polynomials, we'll only use single variable polynomials. Okay, so there's how many? 4 terms. We know what the 4 terms are, right? The 4 terms here are just, the 4 things that are being added. The coefficient of the first term is what? Coefficient of the second term is? Coefficient of the third term is? And of 7? Just be 7, yeah. Which is the constant term? 7. Okay. Okay, give me yes or no on these. I want you to think about these, and you're going to give me thumbs up or down on each one of these. Look at that top one and think about it for a second. Okay, vote. Thumbs up for polynomial, thumbs down for not. Ooh, I'm seeing lots of thumbs down. What disqualified it? 2/5 is fine. The fifth root of 7? That's fine too, because the coefficients just have to be real numbers. And there are no non-real numbers up there, but there's something up there that's causing it to not be a polynomial. What is it? The square root, yeah. Right, remember that the variable has to just be a simple power of a variable, right? We can't have things like square roots. As we're going to learn, maybe you guys remember this, a square root of x is actually x to what power? Do you remember? We'll review this later in the year. Square root of x is really just x to the 1/2 power. Okay, so it's not a whole number power. But if it doesn't look like a variable to a whole number exponent, then it's disqualified. So here's the problem right here. And the answer is no. Okay? Now what about the next one? And take your time. Okay, let's vote on this one. What do you think? Well, I'm seeing lots of thumbs up, and you're right. There's nothing wrong with this one. When I'm dividing by 5 there, couldn't I just divide each term by 5 if I wanted to? And then if I do that, if I simplify this by dividing each term by 5, and what if I put it in standard form? What would I end up getting for my polynomial? Negative 3x cubed, good. Plus 2. That's fine, isn't it? Right, so if I can rewrite it in standard form, then it's a polynomial. Good. Okay, next one. Look at it for a second. Thumbs up or down, what do you think? I'm seeing some thumbs up. I'm seeing a couple thumbs down. How come thumbs down? Because where? Yeah, the x on the bottom is a problem. Because if I were to rewrite that, what power of x is that if I have an x on the bottom? -1. Yeah, and what do we know about the exponents in a polynomial? Can't be negative. They have to be whole numbers, so 0 or positive integers, right? So because this is the same thing as because that's the same thing as x to the -1, that one is a no. Okay. And this bottom one, it's probably pretty obvious. Thumbs up or down? Down. How come? Because cosine of x, does that look like x to a power? No, that's different. That's weird, right? So because it's, I get this term that's not x to a power, this is a problem. Come on, there we go. That disqualifies us. Okay, is that making sense? We get things becoming clearer here? Okay. Okay, so let's take this polynomial. What's the leading term of that polynomial? Good, -1/2 x cubed. The leading coefficient, -1/2. The degree, 3, good. And, okay, so what does this want us to do? Okay, so we haven't talked about this yet. Come back to that. Yeah, so, okay, so we would say that if we wanted to describe this polynomial, we'd call it cubic. Why? Okay, because of this. Here's how we classify polynomials. There's two ways that we do this. We use some words to describe, we use polynomials so much that we kind of have a jargon that's arisen around polynomials. There's some special vocabulary. The degree of the polynomial determines what type of polynomial it is. If it's a 0 degree, we call it a constant. If the degree is 1, we call it a linear polynomial. And I tell you what, all the stuff we've done with linear equations, you didn't know it, but you were working with polynomials. They were just linear polynomials. Okay? So a linear equation is a linear polynomial. If the degree is 2, we call it a quadratic polynomial. If it's 3, we call it a cubic polynomial. Degree is 4, we call it quartic. And if the degree is 5, we call it quintic. And do you use those words, quartic and quintic, very often? Not as much, but you need to know them. And beyond that, we don't give them names because it just gets tiring. Beyond that, we would just say 6th degree, 7th degree, whatever. We also use the number of terms to describe the polynomial. If it's only got one term, we call it a monomial. If it's got 2 terms, we call it a binomial. If it's got 3 terms, we call it a trinomial. And if it's got more than 3, so 4 or more, we don't give it a special name. We just call it a polynomial. Poly means many, right? What does bi mean? 2. What does tri mean? 3. What does mono mean? 1. There you go. Okay. So let's classify these here. What would this first one be? So we want to give it both, we want to classify by degree and number of terms. You use degree first. Okay, so this first one would be a linear binomial. I agree. Okay, everybody good with that? Okay, what about the next one? Quintic trinomial. Next one. Constant monomial. Next one. Cubic polynomial. Good. Next one. Okay, quadratic trinomial. Next one. Okay, give me an example of a cubic binomial. Okay, so I heard x cubed plus 42. Sounds good. How about a linear monomial? I could just do x, but if it's a linear, what power of x is that? Squared, that'd be quadratic though. What's the power of x for a linear? 1. Okay, so it could be x, it could be pi x. I'll just put up there. Okay, makes sense. But the power of x has to be 1 and there has to be one term. Okay. Evaluating polynomials. I mean, this is like, I'm not going to even spend any time on this because you've already done all this. Evaluating a polynomial means you're just plugging in a value of x and evaluating, right? Plug and chug. So that's really no big deal. If I want to evaluate this polynomial at 2, you've already done a bunch of stuff like this. We're just plugging in 2 for x and simplifying using PEMDAS, order of operations. No big deal. If I want to evaluate it at -3, the only really important thing is, remember, anytime you evaluate a function, we always input that value inside what? Parentheses every time. There you go. And if we do that, we'll get 4 times +9, right? Which will give us the correct value for that first term, which is positive. Okay, last part of this now. So we want to talk, we're kind of leading into understanding what the graph of a polynomial looks like. And to get there, we need to know what the graphs of the basic power functions look like. What's a power function? Power function is just a power of x. So the graph of x to the 0 is pretty boring, right? That's just going to be the line y equals 1, right? And so that's just going to be a horizontal line. A linear power function, well, that's pretty simple too. Y equals x is just a line with a slope of 1 through the origin. Okay, here's where things get a little more interesting, and this is what I want to remind you guys about. Now, I'm not sure how familiar you are with this, but it's a pretty simple pattern you're going to see here. So a quadratic power function, x squared, that's a parabola. I'm sure you remember that well from Algebra 1. A cubic power function, x cubed, you remember this one? Have you ever dealt with this before in Algebra 1? Give me 1 to 5 on cubic. You haven't seen that? No big deal. So what does a cubic look like? Well, it looks a lot like if I covered up, if I only exposed the left leg of that parabola, it looks pretty similar to x cubed, doesn't it? But the right leg is flipped around, so it plunges down instead of wrapping back up to the left. What do you notice about x to the 4th? What does it look very similar to? Quadratic. What do you think x to the 6th is going to look like? It's going to look the same basic idea, right? You notice that the higher the power of x, the steeper the walls of the graph and kind of the more squared off the base is, but they all look basically the same. Look at x to the 5th compared to x cubed. Again, pretty similar. Steeper walls and a little bit flatter base, but they're all going to look like that. X to the 7th would look very much like x to the 5th. Just gets a little more severe, right? Okay, everybody see that? Okay. So what could we say in general about these then? If we have an even power function, it's got this behavior, right? It's just going to open up on both sides. If we have an odd power function, it's got this behavior. It's up to the right, down to the left, right? But they're all basically the same. Okay, so the last thing, maybe, I can't remember when are we out of here on Mondays? 20, okay, so yeah, we'll get through this. Okay, so I want to do a little experiment here. Let's take a look at this. Here's a polynomial. And look how small those coefficients are for the bigger powers of x. Can everybody with me here, please? So let's explore this thing and let's see which term most strongly predicts the shape of this graph. Okay, let's just focus in on this thing. I'm just going to go to a Desmos document and we'll look at this here. So here's let's kind of just see what's going on. Here's that polynomial up here graphed, right? Everybody see that in Desmos? Okay. Let's just look at each of these terms individually and compare each of these terms to the overall polynomial. Well, if I expose just the graph of y equals x, look at that. It lines up perfectly with that thing. Does that mean that that's the term that describes it best? Well, in this one instance, but I want you to look at the scale of this graph. What do you notice? Look at the window. It's super zoomed in, right? So when the values of x are really small, in this case, that first term dominated. And why do you suppose that is? Well, look at the coefficients. Look at the coefficients here. These coefficients are really small for the bigger powers of x. Everybody see that? And so when x is small, those were extinguished because the coefficients were so small. It made their contribution tiny. Okay, well, what happens? Let's zoom out and see what happens. If we zoom out a little bit, it looks like it's still just fitting that y equals x. Oh, what do you know? Okay, things changed a little bit. Okay, so turns out that this is very different than y equals x. So we'll cross that one off. As we zoom out, the linear term, we can see it doesn't really help us much. It doesn't look like the linear term. Well, what about this guy? I mean, that looks pretty similar, right? Seems like it matches that quadratic term. Okay, I guess that's pretty good. We zoom out some more. Uh-oh, things changed. Okay. So I guess that quadratic term isn't doing the job anymore. How about the cubic term? Well, that's pretty good. Think it's going to work forever? No. Look what happened. Okay. So eventually it starts to look more like that leading term, even though that leading term has a minuscule coefficient. I mean, look what I'm multiplying it by. The coefficient is this tiny, tiny decimal. If I zoom out far enough, and I'm going to have to kind of rescale this window a little bit. if I keep zooming out far enough, and I had to kind of tame the x-axis a little bit because this thing grows so fast. But look what's happening. If I zoom out far enough, if I get big enough values of x, I mean, those are big numbers, right? Okay, there we go. I think we can see it well now. So look at that. At this point, the function is... I'm kind of curious why we got all this extra conversation going on out here. Is that really what needs to be happening now? Okay, so look at this. I mean, when we get big enough powers of x, where the scale on the x-axis is going out to, you know, like 500,000, right? It looks identical to the actual polynomial, right? They overlap perfectly, okay? And if I go out even further and further and further, they're going to match even more tightly, right? And so what's the moral of the story here? Well, the moral of the story here is for large values of x, the leading term dominates the polynomial. The rest of them don't even matter when x gets really, really big. Okay? We can just ignore all the other lesser terms and only look at the leading term. Okay? So this is what we call the end behavior of a function. What do we mean by the end behavior? Well, what's the domain of a polynomial function, do you think? What's the biggest value of x that we could input into a polynomial function? Is there one? Well, no, it's right. I mean, we could go forever. Now, we can't input infinity because infinity is not a number, but I like the idea. We could let the x value that we input, there's no limit to how big it could be. We can't plug in infinity, but what we can do is in calculus, what we call a limit. We could take a limit as x approaches infinity. Now, can x ever get to infinity? No. But x approaching infinity just means it goes without end, bigger and bigger and bigger, right? As we do that. So if we want to look at huge, why don't you get those Chromebooks closed, everybody? So if we're looking at huge values of x, then think what that means in the xy plane. That means we're going infinitely far out to the right. We want to know what the end behavior of the function is. What is the predictable behavior of the function going to be as x approaches infinity? A lot of times, there's really three things that could happen. It could approach positive infinity. It could eventually, could sweep up to positive infinity, the y value. It could plunge down to negative infinity. Or it's possible it could approach some constant value like 10. It might just approach 10 more and more closely, and we call that an asymptote. And we'll get to those later. That's not really a topic for polynomials, but it is a topic that we'll get to at some point this year with different kind of function. Same thing to the left. There is no most negative number we can plug in. They can get infinitely big. As x approaches negative infinity, we want to know what the left end behavior is like. And end is a little misleading because the polynomial never ends. But the idea is if we go out infinitely far, what's the overall behavior, right? And as we see, it's determined completely by that leading term. As x approaches infinity or as x approaches negative infinity, every term in the polynomial except the leading term becomes utterly insignificant. Only the leading term is going to contribute to that really large scale behavior, which is what we saw in that example I just showed you. And so this is where those power functions become meaningful, right? Because if the degree of the polynomial is 2, then that means the leading term is going to be a quadratic monomial, which means a quadratic power function. If the degree of the polynomial is 3, then the leading term is cubic, right? And so we're going to have these types of behavior. Okay, give me 1 to 5 on that. Does that make sense? If we zoom way out. Now, that doesn't tell us anything about what's going on in the middle of the polynomial. It could be doing all kinds of crazy stuff in the middle, but at the ends, we know what the end behavior would have to be for that function. if we looked at its graph, zoomed out infinitely far, okay? Okay, so there's three things that can happen then. If the Okay, let's look at a quick example here. If a polynomial has degree 2, right? That means that the leading term is quadratic, then we know that it's going to, if we zoom out infinitely far, it's going to look like a parabola, like a quadratic function. If we zoomed in, it might look real different, but zoomed infinitely far out, that's what it would look like. Okay, so the leading coefficient then plays an important role. What does the graph of y equals 2x squared look like? Just show me with your arms what that looks like. Y equals 2x squared. Yeah, it just looks like that, right? The 2 just means it's stretched a little bit, right? But it looks like this. What does the graph y equals negative 2x squared look like? Okay, multiplying x squared by a negative coefficient means it opens down instead of up, right? Okay. So then we got to combine those. Know that the degree of the polynomial is 2, the leading coefficient is going to tell me whether the end behavior is this or this, right? What if the degree were 3, for example? Show me with your arms, you remember, what does a third degree polynomial look like? Yeah, that's this behavior, right? Okay, so what if we have the polynomial y equals 5x cubed? What's that look like? Just going to be this, but stretched, right? But here's the end behavior. How about y equals negative 2y cubed? It's going to flip it then, right? So instead of being here, it's going to be here, right? It flips it around. It reflects it around the x-axis, okay? So that allows us to come up with really just 4 different outcomes. I picked x squared, but I could have picked any even power of x. And doesn't any even power of x, any power function with an even power, don't they all kind of look like this? Right? They all look the same. X squared, x to the 4th, x to the 6th. Any odd power of x is going to look like this. X cubed, x to the 5th, x to the 7th, right? They all look basically the same. So if I have an degree polynomial and a positive leading coefficient, show me with your arms. What's that doing? Yeah, it's doing this, right? We're doing the polynomial dance here. If we have a even degree polynomial with a negative leading coefficient, what's the end behavior going to be? Yeah, there we go. It's down. Okay. How about an odd degree polynomial with a positive leading coefficient? Yeah, okay, that's up to the right, down to the left. Good. And if we have an odd degree polynomial with a negative leading coefficient, it gets flipped. Okay? That tells us a ton right there. That's really, really important because I'll tell you what, a lot of what we do in math, in analysis, like we're entering a part in calculus right now where we're going to focus on just sketching curves. That's sketching graphs of functions using, they don't have to be accurate, they don't have to be picture perfect, but we need to know where the important parts of the function are and what its overall look is, and part of that is end behavior. And so this is something we're going to be reminding ourselves about in calculus like today. So what about number 7? That's a complicated looking polynomial, but what can you tell me about the sign of the leading coefficient and whether it's an odd or an even degree polynomial? So negative coefficient, even. Yeah, and how come? Because of this, right? Because look at the end behavior. It's doing that, right? So this would be negative, even. Okay, how about this one? Positive, odd. It's going to be a positive leading coefficient, and it's going to be odd. It has odd end behavior, right? Okay. Okay, so this is the same stuff. I just want to use the sort of the language of calculus a little bit, just so when you see this in a couple of years, you can draw a parallel to the stuff we're talking about now. If my polynomial function is f of x equals negative x squared plus x. What does this mean? Okay, well this says in kind of what in the language of what we're going to do in calculus, and we'd write this even a little differently in calculus, but what does that arrow mean? It means approaches. So as x approaches positive infinity, or as x approaches infinity, f of x approaches what? And you're going to tell me. Okay, how come? Yeah, what's negative even n behavior? Show me. It's like this, right? So if we're going as x approaches infinity, we want to know f of x is just y, isn't it? We want to know, when we ask what f of x is approaching, we're asking what's the y coordinate as we move along that function towards positive infinity in the x direction. What's the y coordinate doing? Well, the y coordinate is going to be going down to negative infinity, right? So we're going to see this kind of behavior. Y goes down. Okay. As x approaches negative infinity, what's f of x going to approach? Negative, right? Y is going down to negative infinity. Okay, how about this one? F of x equals 1/2 x cubed plus 7. As x approaches infinity, f of x approaches infinity, because we're doing this, right? Positive odd. As x approaches negative infinity, f of x approaches negative infinity. Okay, good. We'll pick this up tomorrow.